So Zipf, let's talk about Zipf. So Zipf is a very interesting character in all of this. He died in 1950. He was only about 50 years old, and he just produced this work, which we'll come back to, which was out of print for a long time. Now you can get it again. It was sort of, you could only find it for like $1,000 at points. So it sort of kind of went away. But he would be fantastic right now. I mean, the way he talks about data and so on and what might be possible with social phenomena is fantastic. Okay, so he noted. So he was thinking about language. So he was a linguist. He was an expert, I think, in Chinese at Harvard, and he looked. One of the things he was doing, I think, in part, was looking at how kids learned, how their vocabulary grew with time. So that was one piece. But then he started to just sort of get excited about everything. So, you know, what's the distribution of city sizes? Like, how much freight goes between cities in the U.S.? You know, articles about other cities in a city, how much they write about other cities, just things like that. How long in inches? How long are articles in the Encyclopedia Britannica? I mean, this is back in the 30s and 40s and so on. And of course, students were the victims here, who had to go and measure things like that with rulers and count and so on. And I do have a piece later on of a comment that was that ended up in a New York Times article from a former student. We'll get to that later. Who was, yeah. So I don't know much more about him, but just his work. Anyway, so we're going to talk about Zipf's law. So Zipf's way is this. This is a very reasonable natural thing. You've got all of these entities would have different frequencies. So it could be cities, and it's just their populations. It could be the words in a book, and it's how many times they appear. It could be species in a forest, and how many counts of each species. So it could be things like this. So you have sizes, right? And that's what we've been talking about. With these power law size distribution, you have sizes of something. You know, how many types of atoms you have in your body. And so this is a simple thing to do. We're going to rank them from largest to smallest, and then just put them on a plot. And so X will be the size of the rth ranked entity. So 1 is the largest size. We want to make sure that we've got that. Could be the frequency of occurrence, right? These are examples. And so Zipf's observation was, in general, that this is pretty common, that there's a power law here for this, that these things decay as a power law. You see this for number of citations for papers, right? The most cited paper going out, which is something to do with protein assays, I think. The first 100, we were talking about how the importance of measurement in science. The first 100 most cited papers, most of them are about instruments and methods, yeah, making science possible. It's very nice.
Good way to build your CV.
What's that?
Good way to build your CV.
Yeah, no, it's true. I mean, you're helping, right? So it's good. Enabling. All right, so something that wasn't noticed for about 50 years, or sort of generally understood, which is kind of odd, it's a pretty simple thing, is that these things look pretty similar, right? So this is, okay, so I've said this. So this is Zipf. This is what Zipf would do for this brown corpus, right? So the word "the" is the most commonly occurring one. So this is just going to be, this is log 10 of them. So it's just going to be ranks across here. So log 10 of 1 is 0. This is the 10th word here. This is the 100th word here, and the 1000th word here. And you're just going to put their frequency of occurrence. So it's a really simple thing to plot. And if you have the data in your, whatever you're using, it's super easy. You just sort it from largest to smallest, and then just plot it. Really easy. You don't have to make one of these frequency distributions. So easy to make. They're decreasing, right? They've got to be decreasing or staying constant. And we can worry about ranks where matching up. Clearly, this is truncated, right? This obviously goes out way, way, way out here. And eventually, you get to words appearing, the hapax legomena, the words that only appear once in the whole corpus. And then you'd have a whole string of ones that all be sitting at the same height. All right, but that's not there. And if you look at this, though, this is the CCDF, the complementary cumulative distribution that we just derived, right? And that is, it looks like a flip of this thing. Right, so the, again, is this little point here. I could make these plots better. The is here, right? That's the same kind of structure here. And that's actually exactly what's going on, right? So these are an important thing. They are flips of each other. So that's the flip of the Zipf plot. So the nice thing then is you can, well, these two laws are connected, right? The size distribution its power law is connected to Zipf's law, right? Very famous. People talk about Zipf's law in a lot of places. And so let's try to understand why that is, and then we'll get a connection between these two exponents, right? So there's minus gamma, there's x, what am I calling? S to the minus gamma for the power law size distribution, and minus alpha was what we'll use for Zipf. I'm sorry, flip around. So we'll use this for Zipfian things. Yeah, good. Okay, so we've got this. So we see this and we think, all right, well, let's work through why that is. So we've got this complementary cumulative distribution. So that's probably right, our sample is greater than or equal to x. So if we multiply that by the number, this gets it back to a frequency, right? This is the number of objects with size at least x, right? N is the total number of objects. And then that has to be its rank, right? So working back from the other end, or +1 or -1. So if there are 30 objects bigger than that, then we'll say it's rank 30 or rank 31. And it's greater than or equal to. So it's going to be the right thing. So yeah, exactly. So we know this is the rank. So now we're connecting. This is the CCDF connected to the rank. So we can write that down. This is the size according to Zipf's law. So this is Zipf's law just sitting here, right? The size of the rth ranked object decays as r to the minus alpha. And we're just going to replace the rank r with this whole blob here, which is from the complementary cumulative distribution. And we know that this beast here has this x to the minus gamma plus 1, right? So it's the minus gamma, we increase it by 1. So we're just going to stick all of that in here. There's a power of minus alpha on the outside. So that's all of this then, x to the r minus gamma plus 1 minus alpha. And what we've got is x to the r is proportional to x to the r to this power. So all of this power has to be 1. So this has to be, right, this blob up here has to be 1. And so this is the connection between Zipf's law and power law size distributions exponent. Power law size distributions and its connection of the exponent. So this is Zipf's exponent. So for instance, when gamma is 2, which is this dire kind of situation where we're just at the cusp of the mean of the distribution being infinity or extremely large, then this is going to be 1, right? 1 over 2 minus 1. And 1 is sort of famously what Zipf thought all of his Zipf laws were. Not all of them. He plotted a lot of things, but he thought a lot of these size rank things were kind of rightly or correctly or by God or something like. He didn't have a reason for these things, right? He had sort of some rough ideas about it, but he didn't have a mechanistic reason. And we'll see in the 50s where reasons start to come out, and we have a nice fight about. We have a fight that keeps going about why it's. Is it randomness? Is it just some sort of simple mechanism, or is it optimization? Is language just kind of optimized thing? Or is it just some sort of growth mechanism that's producing it, or some mixture? And this is not just about language, but cities as well, right? So a city is growing in some sort of random way. Do people just move to New York because they know someone, and that kind of helps connect them? How do social networks grow? Lots of these simple growing things. So this is a very important piece, and it's easy to measure either exponent, but it's easy to work with Zipf distributions. Really, you've got the data, you just sort it from largest to smallest and plot it, and straight away you can see if you've got a power law. Anyway, nice thing to know about. Yes, and as I said, gamma equals 2 is these are very important kinds of examples of Zipf's law and the power law size distribution ones. Right. Okay. So yeah, and out at 3, which is the switch between infinite variance and a finite variance, then this is going to be a half. So Zipf's law kind of tends to float up in that case.